Thanks, everybody. Really excited to be here, and thank you all for coming. So we're just coming from my keynote, and we're going to talk about one of the topics that's really near and dear to my heart. That's part of the multimodal lakehouse, and that is retrieval. And specifically, it is about how to get production quality retrieval. How do we go from that demo that you use vector search for to something that you can ship to your customers and your users, and that really works the vast majority of times. And of course, I'm calling it an art because you'll see in a second. It's not yet a science, and a lot of it is about black magic and trial and error and iterating on your own application and on your own data. So how many of you were at the keynotes just now? Okay, so I can skip the intro, so you guys were all just there. And we talked about this question, right? So, and this is sort of the key connector to the topic today, which is retrieval. And if what really matters about building differentiated AI is connecting your data to the model and to that AI application, then I think you should care a lot about retrieval. And mostly it is about getting really high quality retrieval. So the reason why I'm still calling it an art and black magic is, really nobody still knows what is scientifically the best way to do retrieval. So you see with a little bit of Google search, you get all of these folks that are trying to sell you something around, okay, I have the best course for RAG, and let me just teach you the 25 types of RAG architectures, and 5 different advanced RAG, and yada yada yada. So it's very confusing at times about how you can get from something that gets you excited in a demo, in a POC, to something you can ship in production. And really, I think I boil this down to asking 4 questions. And I think, honestly, if you walked out after this slide and you remember this slide, I think the purpose of my talk is achieved. So we can just finish early. But really, I think there's 4 things, right? Number 1 is, what does your data look like? What is actually being searched over? And what is it that you want to actually connect to the model or the application? Number 2 is, how is the search space constructed? And this is subtly different from the data that's being searched over. It's about how the data is encoded and how is the geometric space of the search constructed. Number 3 is, from the other side, it's not just about the data that you're searching over, but what is the user's intent? What are they looking for? And what are the things what are the aspects about that data they care about? And how is that expressed? And then the last one is actually, I think it's actually the least important, which is, what are the specific techniques that you use to improve accuracy? And this is actually, I think, the easiest part of the job. So I just want to show you a little demo app that we built. The irony is not lost on me. I'm here to talk about production quality. I'm showing you just a simple demo here. But this was something that was super fun for us to build. What we call semantic.art. And so how many of you have used an image generator before? Okay, pretty much everyone. So you're all familiar with the types of interface, right? You get a prompt, and you get the AI generated art, the best that AI can produce in terms of images when it comes back. And so we thought about building a little bit of called a tongue-in-cheek foil. So what we did was we collected Creative Commons licensed artwork from the Met and other public data sets. And this spans artwork from the Dutch masters in the 1500s all the way to modern day master artists. And we made this a searchable data set. So when you put in a prompt in this app, you get not the best that AI can generate, but the best that the human has generated that matches, the prompt. So so something fun would be like, let's see if I still have that prompt. Okay. So something like this, all right? You can. I've got the store prompt just so I don't have to type it in again. Brown cliffs meets so I've got this like poem that's a prompt, and I say, okay, I'm going to try to generate quote unquote artwork that's relevant to my poem here. All right, and so what you're getting is a diverse set of human-generated art from the masters, and then you can look at the information, specific information like the artist, the year, a bunch of tags, and then you can also search by the image itself, and you can find similar artwork like this, right? So I can also, kind of like upload a piece of artwork here. Let's see if I can. Yeah. So I've got this thing on my desktop that's like, Napoleon crossing the Alps here. And just so you can see it, it looks like this, right? And I can search for it, and it'll try to find me things that are kind of similar. And so you get different versions by different people. And then this one's my favorite. This has got a monkey instead. And then of course you can explore that space. So it's not just about finding the work, but it's actually exploring this artistic space. So I thought it was really interesting. And building this app was really edifying because it's not just about, okay, I take images and I turn them into vectors and then I make a search. Because what the user is looking for can be completely different. They could be looking for the mood, maybe a color palette, maybe the subject, maybe some tags. And if you just have an image embedding, it's very hard to capture all of that. So it's not just about so building that sort of accurate and more sophisticated search. It's about two sets of problems. One is how do I actually generate the types of features that I want, right? So this is the data that you want to search over. And then how do I take what the user is asking for and really discover the intent? Like what parts of their query is about the color palette, is about the mood, and maybe about the artist or the year or something, like the era and the style. And then, the second question is about the search space, right? That's the part that kind of connects this user intent to the features of the data that you're searching over. And then we can take a look at how we actually combine all of these using search methods like filtering and hybrid search. So let's get back to the presentation, and we can talk about this, right? So first of all, for a given piece of artwork, there's a ton of multiple representation. So there's a sort of a literal description of what actually this thing is and the subject. There's an artistic description, maybe a color profile, and then of course the image itself has different features. And then the description, the text description also has features that you want to encapsulate. So all of these things can end up being searchable. And so the process that we go through with LanceDB is, we start with the data that's being searched over, which is the source artworks, and then we generate a ton of features that make it more searchable and more easily searchable. So generate a caption that is basically the poem, natural language caption, that's more the literal description. And then we use, and these are both done using the models. And then there's a mood keyword where we extract from the captions that we store for filters. And then of course the image content itself. All right, so the next thing is to construct the search space. It's about constructing the embeddings, right? And then these can be generated directly from the text or directly from the images. And then of course we can capture the full text search indexes on the mood keywords and generate filters and allow that search to be not just over the vectors, but also the plain text themselves. So we can store all of that. It's very easy to do that in LanceDB. I'll send out the code later for how we do it, and you can take a look. It's a couple lines of code to add it to the database. And then we also have fairly simple code to generate each of these features. And so the second thing is the embedding space, right? So when we talk about building these search applications, we sometimes talk about fine tuning and RAG, and we talk a lot about fine tuning the LLM for the generation step. But what's interesting also that not a lot of people consider is actually fine-tuning the embedding model itself. And actually fine-tuning the embedding model is a lot simpler and gives you a lot simpler than fine-tuning the LLM. And it gives you pretty good results. So this is an experiment that we ran. Baseline non-fine-tuned embedding model hit rate at 5 is about 48.75. And we get about 10% better hit rate just by, this is roughly 6 epochs of fine tuning for this fairly small embedding model. And what's not pictured here is you actually don't need a ton of observations, not like what you need with fine tuning LLM. It's just a lot simpler, and it requires a lot fewer observations to get substantial lift. But this recommendation is still that you start by using RAG tricks and feature generation, and you only fine-tune the embedding model when you have data and you know something about that data, the structure of your data, and then you have confidence that's going to work. So generally, the recommendation here is this. So if your application and the types of questions and answers are very generalized text, so ones where your application and your data, the distribution looks very similar to generalized training data for that model, then you're not going to get as much lift. But if you have domain-specific questions and answers and domain-specific fine-tuning data, then you're going to see really great gains from fine-tuning your embedding model. I think last year there was an interesting phenomenon where lots of folks were advocating for using just synthetic data to generate or generating synthetic data to do fine-tuning for the embedding model. And we've done a bunch of experiments. We feel like that's in general not a great recipe for success, especially if you have kind of if your prior is about what the user's queries are going to be is not very good, right? So basically, if you start with a shitty data set and you don't know anything about what you're going to actually encounter in production, and you generate a bunch of additional data that looks like your original data set, you're not going to get great results. All right, so now we come to kind of question number 3, which is the user intent, right? So we've generated a bunch of features, and maybe we've fine-tuned the embedding model for one or more of these features, And now when we build that application, the user starts asking questions. But how do you know which of these columns that you want to search over? Or more specifically, like how do you know which part of the user query is going to target which of these features? So this is where we call this as LLM as semantic router. This is where query parsing, query rewriting comes into play. So with semantic.r, what we've done is whenever you have a user query, we don't embed that directly. We actually use an LLM to parse that query and to extract the relevant parts for the relevant features and the relevant search indexes. And then we can actually use that to route the right components of the user query and the right intent to the right places in the feature set. So, at the end, this is what the query pipeline, the semantic routing, looks like in action, right? So, once the user can input some text, right? You saw that poem. The user can upload an image, right? That was the Napoleon image, or you can actually do both. So with the LLM, we can extract from the text. We can extract the mood that goes into the mood keywords as a pre-filter, and then we can use the images branches that extract the query style from the input image, and then anything that's like the caption image, and then we end up rewriting the query as well to help extract the mood. But finally, we do a hybrid search that can search over multiple embedding columns, multiple indexes. And then at the end, if you have multiple result sets, you have to combine them somehow, and then you want to be able to re-rank them so that the most relevant results actually boil up to the top. Right? So the search techniques that is being used here is mainly hybrid search, which is augmented by the pre-filters, and then is being improved on in re-ranking. So with LanceDB, of course, this is really simple actually. So it's if you want to search if you want to do hybrid search, you can just say .vector and then .text, and then if you want to do re-ranking, just do .rerank. You can add your own re-ranker, right? So there's a couple of different re-rankers that you can use. One is you can just call out to a third party. So this would be maybe like a Cohere re-ranker or something like that. You can have the plain reciprocal rank fusion re-ranker, where it's just a simple arithmetic calculation, and it's not it's the fastest because you don't have to ship your data anywhere. But what's probably the most interesting, and I'll show it here, is you can pull any model off of Hugging Face and essentially turn that into a re-ranker. And you can actually also tune the re-ranker itself. So if you look through, or if you summarize all the experiments, vectors, what we found was interesting. So vector search performance improved very significantly if you use re-ranking. And it's up to 12% improvement at the top 5. But for full text search, actually re-ranking didn't show as much. So and it's not just like worse across the board, but it's just not very stable. So some of these models, some of the data sets were showing maybe like up to 20% gains, and others actually made things worse. So we can take a look at the re-ranker models. So the re-ranker models, when you pull them off of Hugging Face, these are essentially models that are not used for re-ranking, right, by default. So we're calling them untrained, and so if you use them for re-ranking, the performance is actually terrible. So this is like single-digit hit rate here. But with maybe a few hundred observations, and these are just ranking pairs that you don't need anything complicated, you can actually get pretty good fine-tuned re-ranker performance. So, and you can get pretty good results from these specifically trained to be re-ranker models itself. So at the end of the day, if you're thinking about improving your hit rate over time with retrieval, right? It's easy to combine fine-tuning both the embedding model and fine-tuning the re-ranking model, and these things are a lot simpler than fine-tuning the LLM itself, and you get pretty substantial improvements in your hit rate. So the way to think about it is, start with the, I would call it more deterministic, non-model based improvements. So generating the right features and understanding and parsing user query and user intent, right? These are not machine learning techniques that you need to do. These are things, it's about understanding the problem domain, understanding your data domain. Then when it comes to improving the search based on the right framework, then these are the techniques like, using hybrid search, using filters, using re-ranking, and then fine-tuning your embedding model and re-ranking model. And so that's sort of the progression that we generally recommend to our users. And the thing that we don't have time to cover today is actually sort of the what to do beyond that, because it's not just a linear process. You do the A, then B, then C, then D, and then you're done, right? This is basically one loop in your iteration, and you're gonna have to constantly improve that over time. So the thing that really ties it all together, which unfortunately we don't have time to cover, is how do you set up the eval data set, and how do you iterate over time, and where do you store that training data, fine-tuning data? But I think that's a topic for another day. All right, so I'm just going to repeat this slide here because I think it's super important. It really gets to the heart of how do you go from demoware to production quality retrieval. All right, cool. So thank you for coming to the talk, and I just want to say join our Discord community, and then also we're hiring. So if building applications or retrieval and specifically building databases for these things is interesting to you, let us know. Okay. I'm not sure when I think we're right at the end of time, but maybe if you have questions, we can take a couple.
Yeah, thanks for the talk. Do you think more data will help? Not LLM kind of data,
Yeah.
but significantly more, like 10x more?
In terms of like fine-tuning performance, yeah, there is some diminishing returns, but like certainly a lot more data helps, and I think it's more about it's less about the quantity of data, but the quality of data and the distribution of data.
And that's actually my second question. It felt like you were describing different features. If someone wants to have the same looking picture, or wants the same context kind of picture, or wants the same color palette of pictures, or art style, isn't it easier to make buttons on your website which says, I'm interested in this or in this or in that?
Yeah, you can certainly do that. So I think but at the end of the day, those buttons, if the user is making those selections, they're essentially expressing intent in terms of like filters, right? Those get turned into filters. And number two is a lot of times users don't necessarily know what they're looking for, right?
So they try three.
Yeah, so they might try different things, or they might just say, or they might give up if you have like a ton of options. You might just give them something language-wise to search.
So if you make it generalized,
Yeah.
you should have some iteration
Yes.
in steps,
Yeah.
which are also filtered.
Yeah, you can basically also discover more user intent through this iterative user interface. But yeah, so I think at the end of the day, I think this is a great question. Is at the end of the day is not just about this underlying search technique, but also what the search experience, the discovery experience look like for the user to help them to help them express what they want a lot clearer. Yeah, great question.
Can you talk more about the most important struggles or pitfalls you had in fine-tuning data sets?
Oh, I mean, I think the biggest one was like we went in thinking that just synthetic data would do it, and we just couldn't make it work, and it felt like because we were seeing a bunch of things on Twitter that people had really great experiences with just generating synthetic data sets, and it took us a while and asking around a lot to figure out like that wasn't happening, or maybe that was the exception to the rule. Yeah, so that was the big one. But a lot of the other things, it's drawing parallels, like fine-tuning the embedding model, and especially the re-ranker. It's much more similar to training like a classical ML model than like fine-tuning an LLM. And so we had to kind of go back to the previous mindset and techniques, right? Like, how do you construct the right positive examples versus negative examples? What is the ratio of positive to negative examples, and like what are the right metrics that you use, and there are subtle differences. So for example, if you're training like a recommender system, like if you think Netflix, right, that top left corner, right, the number one spot in a list of 10 recommendations, that number one spot is worth a lot more than the following 9 put together, right? So the ranking, the specific ranking, especially at the top, is super important for recommender systems. But for RAG, if you're feeding the top 5 contexts into the model, the specific ordering at the top is less important, right? As long as the relevant context is within the top K that you're gonna that's within the context window of your model, then I think that works.
So how do you generate the metrics or the formulas that you use right now for ranking?
So we're using hit rate. So like we're not necessarily using like we looked at like NDCG and more classical recommender system metrics, but this one works fine. So okay, well maybe one last question. I think folks are waiting for the next session.
Thank you for the presentation. For fine-tuning the embedding model or re-ranker, I wanted to ask how many data points you have for refine.
I think with a re-ranker, like if you have as few as a few hundred observations, you can start to see gains. With embedding models, like you probably need a few thousand. But like if you're able to gather like 10,000 data points or something like that, that's like of decent quality, you're gonna see a pretty good lift there.
One follow-up, did you guys have used that parameter efficient fine-tuning?
Sorry, what was that?
Have you considered parameter efficient fine-tuning for this purpose?
I mean, for this example, I think we kind of just did a simple sort of sweep. But yeah, I mean, I think there's a lot more that you can dig in, yeah, to get the maximal lift for your fine-tuning process. Okay, all right, thank you so much. Really appreciate it. Yeah, and join our community if you have more questions.